right, this is going to be the third and final video in chapter 14. Okay, so we said that temperature was one of the factors that affected the rate. And as the temperature increases, that means the reaction proceeds faster, so the rate also increases. And the rate constant is dependent upon that temperature. As the temperature increases, so does the rate constant. And as a general rule of thumb, the rate constant doubles with every 10 degrees increase in temperature. Now, the collision model, or sometimes called the collision theory, is based on the kinetic molecular theory, so that molecules have to collide in order to react. And if there are more collisions, then that means the reaction is going to occur faster. And likewise, if there's more molecules, then we're going to have more collisions and the reaction rate is going to be faster. So in a chemical reaction, the bonds are broken and new ones have to be formed. That means that the only way in order to form products are to have the reactants collide together, break those bonds, and form new ones to make the products. And in addition to the collisions, they also have to have the correct orientations when they collide in order to make the products. Okay, when we talk about them having the right orientation, there isn't a lot that we can do about that. So it has nothing to do with the amount of energy. Increasing the energy doesn't make them have the proper orientation. There isn't really anything that we can do as far as the orientation is concerned. So we just want to make sure that we have lots and lots of collisions so that at least some of those are in the correct orientation. All right, now that minimum energy, or that threshold that the reactants have to meet, is called the activation energy. Once they reach that activation energy, then they can make products. And if we think about this golfer, this would be the activation energy. So the reactants have to at least get to that threshold before they can form products. Now, once it says the reactants must gain energy as it proceeds until they get to that maximum energy state. That maximum energy state is called the activation energy. That's the amount of energy that they have to overcome. And whatever the organization of the atoms is at that time, that's called the transition state or the activated complex. And the difference between your starting energy and the energy at that hill is the activation energy. We'll see that in a graph here. Okay, so here is my reactants. This is my products. The difference between the reactants and the products is the change in energy. This could be exothermic or endothermic, depending on whether you're gaining or releasing energy. Since in this particular reaction, I ended up with less energy at the end than what I had at the beginning, that means energy was released, so this would be exothermic. Now the activation energy that we're talking about is the energy from the beginning, the reactants, to the top of the hill here. That would be our activation energy. And the species that's present up here, that is that activated complex. So this is a reaction progress diagram. The rate constant depends on the amount of the activation energy. All right, now, there are several different molecules in a reaction. They have an average temperature, but they don't all have the same temperature. So if we are at a higher temperature, that means that more molecules are going to have they're going to meet that threshold in order to make the reaction occur. So if we are at a higher temperature, we have higher energy and more of the molecules, we're going to have a higher proportion of molecules that are going to meet that threshold. All right, so in here we have three different reaction progress diagrams. They have differing activation energies. So this one is 15, this one's 25, and this one's 20. And they want me to rate the forward rate constants from the smallest to the largest, assuming they have the same value for the frequency factor. Okay, so we don't care about the delta E. The delta E doesn't have anything to do with the rate. The only thing that affects the rate is the size of the hill. So this one has the smallest hill. This one is next, and it looks like this one is the highest amount, which means this reaction is going to be the fastest next, and then this one would be the slowest reaction because it has the biggest hill. Okay, so the lower the activation energy is, meaning the smaller that hill, that means the larger the rate constant and the faster the reaction. So the value of delta E, we said that had nothing to do with the reaction. So the order of the rate constants for that previous graphs would be the second, the third. So the second one would have the lowest rate constant, then the third one, then the first one. All right, activation energy is involved in what's called the Arrhenius equation. And this is the Arrhenius equation. So we have K, which is a constant, the rate constant, A, which is that frequency factor, E is the opposite of the natural log, EA is my activation energy, R is my ideal gas law constant, and T is my temperature. Now, if I rearrange this equation and I show it like this, that means that this looks like the equation for like y equals mx plus b, which if I would make a plot of ln of k on one axis and 1 over t on my other axis, then that means the slope of the line would be EA over R. So I could find my activation energy by graphing it as well. And if I have two sets of conditions, because let's say I don't know K, so I would set this at one set of conditions equal to this at another temperature, and then I would have this equation, which is for two conditions, like one at one temperature, one at another temperature. All right, so this is a graph showing that I'm plotting ln of K and 1 over T, and notice the slope is negative. That's why there's a negative sign, because it's going down. Slope is EA over R. So that means if I were to plot this in graphical analysis, I could do a linear fit on this. It would give me the slope of the line. And if I multiply the slope by R, that would tell me my activation energy for the reaction. All right, last part of this are reaction mechanisms. So the mechanism is the steps that it goes through. All right, and if a reaction that goes in one step, each individual step is called an elementary reaction. And the molecularity tells me how many molecules are involved. So if it's unimolecular, I have one molecule. Bimolecular is 2, and termolecular is 3. Okay, so here's a table that shows me if it's unimolecular, there's only one. If it's bimolecular, this could be A, which is second order, so that's 2 of them, or it could be an A and a B, that would be 2. If it's termolecular, that could be A cubed, because that's 3, or 2 and 1 would be 3, or 3 different ones. And termolecular ones are rare, although they do occur. These are usually slower than unimolecular and bimolecular. Most all of the reactions that you'll see are unimolecular or bimolecular. Now, what limits the rate is called the slowest step, and that's the rate determining step. So just like in a relay, your time is never better than your slowest runner. So if I have several steps, the rate determining step is that slowest one. All right, now the rate law has to be derived from the rate determining step. And that rate determining step is the slowest one. And each step has to balance, just like any other equation. All the intermediates should cancel out to show that they're used up. And the stoichiometry should be when all steps are added up, meaning we're going to combine all the reactants together, all the products, and cancel out any of the intermediates. And any catalyst that is there should be used, and then we could reuse it. We should be able to extract it when it's done. All right, so here is one where they give me a reaction. This is the proposed rate law, which says that it's second order with respect to NO2. So a proposed mechanism is the one shown below, where this is the rate determining step and the second step is faster. And we can see that we form NO3, but it's used up in the next step. So that means NO3 is an intermediate. All right, so if I were to add up everything that is the reactants and add all the products together, so here's the one reaction, here's the other reaction. When I cancel out the NO3, then this, and this NO2 would cancel with one of the NO2s, but this would be the reaction that the overall reaction. So this means this is a possible one. Now the intermediate is not a reactant, it's not a product, it's not the transition state. So here you can see we have two transition states, and then the intermediate is in between of those. The intermediates are stable, and they occur along the pathway, and then sometimes it's possible to extract those in order to isolate. You can extract them and isolate them. All right, now sometimes the rate determining step is not the first step, it might be the second step. So in this case, the proposed mechanism shows a fast step at the beginning, and then the next step is the slow step. The rate law should include the ones from the slowest steps and all of the ones before it. All right, in this particular problem, they give me this proposed mechanism. It wants me to describe the molecularity of each elementary reaction, write the equation for the overall, and identify any intermediates. Okay, so the first reaction has one molecule, so that would be unimolecular. The second one has two different molecules, so that would be bimolecular. The rate, write the equation for the overall reaction, so I would add this side together and add this side together, and the O's would end up canceling out. So in this case, this is showing what it looks like all added up. When I cancel out the O's, that means this is what I end up with. So this is the net equation. And then the O is the one that we canceled out because it was a product in the first step, but it was used up in the second step. So that means it is the intermediate. All right, now catalysts are something that lowers the activation energy. So you can see here we have the uncatalyzed reaction, and the blue one is the catalyzed reaction. So it is something that we add that only changes the speed of the reaction. It doesn't actually undergo a change itself, and it can be used again. So it lowers the activation energy. And these catalysts can either be homogeneous, meaning the same phase as the reactants, or they could be heterogeneous, meaning they are in a different phase than the reactants. And that's going to be the end of chapter 14.